is largely lost. It used to be something that was part of geometry, but it is no more. So it hasn't been for a while. So it's not particularly hard if you are good with your trig. If you're not good with your trig, then this can be very time consuming. I don't want to spend an inordinate amount of time on this, but I have found that students need more assistance doing this than they used to. So again, I am counting on you guys to pick this up quickly. I will give you a framework to do this, but if you have trouble with trig, then you might want to have your trig crib notes out somewhere, because there's a lot of triangle crap in this. I mean, it's all triangle stuff. So I will provide you with what I think is a sequence of steps. But some of you are probably good at this already and do not need to do all the things I'm going to show you. There are dozens of shortcuts through the work I'm about to show you. But I'm going to assume you don't have those shortcuts. Now, for this particular unit, what we're going to do is unlikely to ever show up on a test. But it applies directly to any vector, and it will show up when we cover momentum, two-dimensional collisions, three-dimensional collisions, and three-dimensional force problems, and two-dimensional force problems, which is all of them. So it applies directly to those. So I'm going to talk about relative motion and the addition of vectors, but before I even jump in, I have to throw out some rules from the very start. These aren't steps, these are just rules. You can only add like vectors together. You can only add vectors that are of the same type together. So you can add a velocity and a velocity vector together. You can't add a velocity plus a displacement vector. Velocity and displacement are related, but they're not of the same type of vector. You wouldn't add them together. Velocity affects displacement, and that's different. You need to express your vectors in the same coordinate system. So we need to decide what that's going to be. It doesn't matter what kind of coordinate system you choose to use. As long as you apply it uniformly to everything in the problem, you'll be fine. If you don't, and you're not thoughtful about it, you'll be in trouble. And last, this applies to all vectors. So you need to know whether you can apply it in your circumstance. So the issue comes down to something like this. And let me give you an example. You walk 3 meters at an angle of 30 degrees west of north, then 5 meters at 40 degrees south of west. How far are you from the start? You guys all probably, hopefully agree that you're not 8 meters away. I mean, even if you don't fully understand all the information that's up there, it sounds like you walked northwest first, and then it sounds like you walked a little bit further in the southwest part afterwards. You understand that the distance from here to here is probably less than 8. Are we all in agreement there? Adding vectors means you have to take their direction into account. And although for the time being we had said that direction meant just forwards or backwards, we can do more than that. We do have the capacity to work under conditions where we have 2 and 3 dimensions. The issue for you is that you probably don't have any mathematics that directly allows you to add vectors that aren't in 1 dimension. So you need a method to add these together. And the method's not complicated. You could do it graphically, meaning you could, with a piece of paper and a protractor, just draw this out. And if I thought we had enough time, we would do that first, which is why you have a protractor as part of your toolkit. And I would very much like to have done it. I tried to bring this up the other day, and I think I failed. I'm not even sure I brought it up in this class. But the class I did bring it up in, I got some odd responses. I bring this up because of the thing that Olivia said. Do I put in -20 when I do the sign? It's been ingrained to you guys to follow a certain set of rules in your math class. I can't break them. I'm not going to try, but I need you to understand why those rules are not of use to you as much as you'd like to think. First, I'm only going to give you angles between 0 and 90 degrees. For any of these problems, you're going to get 0 and 90. That doesn't mean that they won't be in any of these quadrants. They could be in any of these. As long as I give you proper reference, between 0 and 90 could be in the second quadrant. As long as I tell you that that angle is relative to what you would call positive y or what you would call negative x. So if I tell you 30 degrees to the left of positive y, you would know what I meant. Your math class would have you believe that all angles start at 0 here and can only be measured in this direction. And therefore, if you measured one that was negative, it was starting in the 4th quadrant. Right? This is what your math class would have you believe. And they would also tell you then that in this quadrant, sine is positive and cosine is positive. In this quadrant, sine is positive and cosine is negative. Do you guys remember this stuff? Those of you who have passed through this? That's a way of teaching that works great if you're always using the same coordinate system. The rest of the world doesn't work like that even a little bit. I said to you guys, and I will reiterate, that although this might be 90 or pi over 2, if you've done this already, you know why I'm saying that. If you haven't done this already, don't worry. You'll do it in pre-calc, or maybe you won't. Maybe they finally gotten rid of the unit circle. But I doubt it. But I also know that this is north, and it is also 0 degrees on every map taught in North America. And this is east, and it's 90 degrees. And if you understand this part, and people didn't when they left here, that suggests going this way increases the angle. Do you see the problem? Because although you might call this 270 degrees, on a compass, it's 180 degrees. And is also called south. So no, we are not going to use what you did in your math class the exact same way. This also brings another problem with what you learned in your math class. You learned x is always coming from cosine, and y is always coming from sine. Please throw that away. Don't even start it this way. You will be in trouble. We determine the coordinate system that we apply to our problems. And that's collectively, us. We determine it. Because we're the ones who determine it, we can choose the system that best suits our needs. In doing these problems, the very first thing you should do is identify any given vector. Well, I'll say any and all given vectors. Okay? That's the first thing you should do. Now, this problem clearly identifies two vectors, the 3-meter vector and the 5-meter vector. We will write them in a certain manner to convey that they are vectors, but only for this portion of the unit. We won't write them like this afterwards. The first vector is 3 meters long. And then we write this kind of upside down division symbol to separate the magnitude of the vector from the direction of the vector. And I'll write the direction separately, 30 degrees west of north. My next vector, 5 meters, 40 degrees south of west. All right, so I've identified any and all given vectors. These are both displacement vectors. Now, the second thing you have to do, after you've identified your vector, you need to use a consistent and agreed upon coordinate system. Now we're going to apply this coordinate system to the entire problem. We just have to figure out which one we're going to use. Now, I think it pretty clear that we're probably going to have to use one that has north, south, east, and west in it. And there's a convention associated with north, south, east, and west. So let's start by recognizing that by convention, we generally write north as upwards. Now, it really wouldn't matter what direction we made upwards, as long as we lined up east, west, and all the rest of them in the way that has already been agreed upon. But let's, for our problem, go ahead and say north is upwards, east is to the right, south is downwards, and west is to the left. I don't mean to insult your intelligence, but I asked for students to do this in one of my other classes, and they put them in the wrong places. So they had switched west and south, and that's going to be a problem, right? But you're not done. This isn't the part that I really worry about. The part you have to also do is remember you are only capable of doing one-dimensional mathematics. So what do you want to put for positive and negative in each of these directions? For example, if we choose to make north positive, we are saying also that south is negative. If we choose to make east positive, we are saying that west is negative. This is a convention. We are choosing how we want the convention to play out. Now, when we go to forces, we won't necessarily do it this way because I would always encourage you to make the positive direction the direction of motion. And that can be any direction, which is why I don't want you to get attached. We're just using north, south, east, and west because it works to break what you've done in the past. So I'm good with this, but any coordinate system you want to use is fine. And I'm going to apply it to both portions of my problem. Now, you might not know what I mean by that, but it'll be made clear right now because we only have one-dimensional mathematics. So the next thing that we have to do is break up our vectors into their component amounts. So break up our vectors into their components. Aligned with our coordinate system. I need to emphasize that component is definitely a vocabulary word. So when I say that we have to break our vectors into components, two vectors define another vector. But when I say that we're going to break them into components aligned with our coordinate system, our two component vectors will be aligned with the north-south direction and the east-west direction. For example, let's start with our first vector. 3 meters, 30 degrees west of north. Some of you are seeing this for the very first time. So here's how you read the statement. It says a plane needs an airspeed of 75 meters per second. That's the airspeed of the plane. To land on a windy day. The plane is going to land on a runway that is due south. So I need the resultant vector to be due south, no x component, only y components. With a crosswind of 20 meters per second, heading 75 degrees west of north. And then I have a collection of questions. What's ground speed? What's the angle? Heading of the plane, and what is the braking acceleration of the plane? Let's start with the wind. The wind, 20 meters per second, 75 degrees west of north. So 20 meters per second, starting from the north, turning towards the west, 75 degrees. Now look, some of you didn't do that. Do we see why I made that decision? Do you see why? Start with the last thing, turn in the direction, the number of degrees they indicate. I need to know how much of this wind is blowing to the west. That's the part that's blowing the plane off course. And I need to make sure that the part of the wind that's blowing north isn't faster than the plane can fly. So I'm going to break this up into two components, a vertical and a horizontal. And I'm going to remind myself that this is 20 meters per second. So I want the x portion and the y portion. Seems to me the x portion is the opposite side. You guys agree with that? Alrighty. So I'm thinking my x portion is going to be 20 sine 75. And my y portion is going to be 20 cosine 75. Well, this part's just a calculator. 19.3 5.18. Any question about that? Well, it's negative in the x direction. So negative 19.3 in the x hat direction plus 5.18 in the y hat direction. That's the wind, just converted to rectangular coordinates. The plane needs to fly due south. This part has been the part that I've had the most difficulty convincing some folks how to deal with. Not exactly sure why. The plane is being pushed this way. But the plane wants to go that way. Well, seems to me that if I want the plane to travel along the red arrow, and I know the blue arrow is pushing it off course, I'm probably going to need to fly this way. Does that make reasonable sense? I need something that's going to push the plane in the positive x direction. That's it. That's all there is. The plane has an airspeed of 75 meters per second. Those are going to be my components. The issue is that I don't know the angle. If I use that as my angle, though, I could come up with an expression for the x portion and the y portion. The x portion based on sine and the y portion based on cosine. So my x portion will be 75 sine theta, and my y portion will be 75 cosine theta. Looks like my y portion is going to be in the negative direction. My x portion is going to be in the positive direction. So I'd probably list that as negative. So if I was to write out a vector equation, I'd put 75 sine theta in the x direction minus 75 cosine theta in the y direction. Which one of these do I want to zero out? X. I want there to be no component in the x direction. I want that sum to be 0. I don't know what the y will be. That will be the ground speed. So it looks like I'm going to have negative 19.3 plus 75 sine theta will be equal to 0. So theta, 14.9 degrees. Any question about that? That's not the answer. If you want the answer, you need to say 14.9 degrees east of south. That's the answer for the heading of the plane. Now, we're not done. We want the ground speed of the plane, and that's going to be this sum. So 5.18 minus 75 cosine 14.9. All in the y direction. That gives me negative 67.3 meters per second in the y direction. Somebody complained that it was negative last class period. I have no complaints that it's negative. I wanted to land towards the south. That makes perfect sense. I expected my answer to be negative. If I got a positive, I would have a problem. So, it asked for the ground speed. So the ground speed is just 67.3 meters per second. What braking acceleration would be required? Well, I need to bring that initial velocity down to 0 in a displacement of 600 meters. I think I can probably find the acceleration from a motion equation. Seems like the most likely way to do it would be 0 squared minus 67.3 squared equals 2a times 600. So a ends up being about 3.9 meters per second, or sorry, 3.8 meters per second squared. I got 7.7, but I'll say 7, I don't care. If you had decided to put your to put your triangle like this. So something like that. We're going to get the same answer technically, but you're going to get this triangle. You're just going to get the complementary angle, but you'll list yours as south of east instead of east of south. But you'll get the right answer. You're just going to have your components on your sine and cosine attached to different sides. But it works out. It doesn't matter which one of these you actually do. I'm getting this question a lot late in the game. So you're right. We set the x components to 0. We decided that the sum of these two had to equal 0. Right? We introduced the 0 to this problem. Like, we brought it here because we know something about the answer. What do we know about the answer of the plane? What does the plane have to do? I'm asking what the plane has to do, what direction it has to fly in order to be on the runway. Seems to me that the problem tells us that the plane has to be moving due south. The problem told us this. So in the end of the day, when I add the wind to the plane, can it have any component of velocity that is not towards the south? If we have a component of velocity that is in the x direction, the plane will not travel along the runway. It will fly onto the side of the runway or off the runway. Does that make sense? So we're trying to figure out how big does this angle have to be so that this component of the plane's velocity perfectly counters the wind's component of the velocity in the other direction. Does that make sense? So we are purposely, again, we choose to set that equal to 0. We choose those things to add together to be 0 so that the result of the plane and the wind has no x component, so it's flying perfectly in the north-south direction. Okay. Sophie? All right, number 5. A plane is attempting to land on a runway that is due west. The wind is blowing 25 meters per second at an angle of 30 degrees north of east. The plane has to maintain an airspeed of 100 meters per second to land successfully. This question? Okay. So, the first vector seems to be the wind, as given to us as 25 meters per second, 30 degrees north of east. The plane must maintain a speed of 100 meters per second, but we don't know the direction of the plane. But we do know that the plane has to land on a runway that is due west. So ultimately, the sum of the vectors, my resultant vector, will be some speed in meters per second, but due west. All right. If I draw the wind out first, using a coordinate system that is aligned with north, south, east, and west, go. So the wind, 30 degrees north of east. Starting at the east, turning towards the north, 30 degrees. I did have a student yesterday who actually asked me why she couldn't just always make all the x values related to cosine and all the y values related to sine. Do we understand why that can't be true all the time? Like in this one, that will be true because the angle is relative to the horizontal axis. But if I make the angle relative to this axis, that's suddenly not true anymore. So we can't just always assume that. And that's one of the things we will look for when grading, to see if you have your coordinates flipped, because that's what happens when you assume that. But either way, in this problem, I can break the wind up into its two components by placing a triangle around the angle and using that triangle to figure out the two components. If this is 25 meters per second, then the y component will be 25 sine 30 degrees, and the x component will be 25 cosine 30 degrees. Looking at what quadrant that's in, they're both going to be positive. So I'm thinking, let's see, 25 times 30 cosine gives me 21.6 x hat plus 12.5 y hat. The plane has to travel purely in the east direction when it lands. I think the only way that can happen is if some component of the plane's velocity is downwards to counteract the wind. And then the rest of the plane's velocity needs to be to the west in order to be traveling to the west. So I think we need a vector that looks something like this for the plane. Any question about how I came to that conclusion? I need the plane to be going a little bit to the south because the wind is going a little bit to the north. But I need the plane to also be going to the west because the runway is to the west. So I need something that goes both south and west. I could probably come up with a third way to say it. You sure? Excellent. You're welcome. I'm indifferent. I just want to make sure everybody understands. I, again, don't care how we draw the angle, but I'm going to draw the angle this way just because I feel like it. So that means a component like that and a component like this. And I know that the plane's airspeed is 100 meters per second. Somebody cracks open a beer in my class. Way to go, Cammie. Now, again, part of this is going to be in the x direction, part of this is in the y direction. If I'm using this as theta, then it's going to be west of south in my final answer. Go ahead. My y component will be 100 cosine theta, and my x component is going to be 100 sine theta. That all right? They are both in the negative direction because this particular thing is in the third quadrant. So I would write this as negative 100 sine theta minus, in the x hat direction, minus 100 cosine theta in the y hat direction. All good? Now, our plane is going to fly purely to the west, or at least we want it to fly purely to the west. So when I bring these things together, I need to eliminate a component that would take it out of traveling in the west direction. So I'm thinking I would eliminate the component that's in the y direction, since that would be making the plane travel north or south. So I am going to intentionally add up the y components and set them equal to 0, so that the components of those two velocities cancel out, leaving the plane purely to travel in the west direction. So that means negative 100 cosine theta plus 12.5 equals 0. I should be able to figure out an angle that will provide that amount of y direction stuff. So looks like 0.125, find the inverse cosine, and I get theta equals 82.8 degrees. Now, going back up here, that means I need to point the plane 82.8 degrees west of south. But somebody's bound to give me 7.2 degrees south of west as their answer, because we know that they could draw their triangle the other way, and both of these would be okay. All good? I'm pretty sure the sine of 7 degrees is going to be 0.125. Now, that's not the full answer, but it gets us close. If all we wanted was the direction of the plane, we'd be done. But it says, what will its ground speed be as it lands? Well, that's going to be the sum of the two vectors that are in the x direction, because the plane is pointed in such a way that it's not even headed down the runway, but part of its velocity is to the west, but part of the wind's velocity is to the east. So I'll take that negative 100 sine 82.8 plus 21.6 is going to be my total velocity in the x direction. I get negative 77.6. Since it only asks for a speed, 77.6 meters per second would be the ground speed of the plane. And then you should assume there'll be some other question to follow up after that that asks, like, how long does it take the plane to stop if it has to stop in 300 meters or something that's going to follow up here. All right, for number 4, we have to add all of these vectors together and produce a resultant. So we'll just take them one at a time. And let me just make something here. How many are there? 1, 2, 3, 4. Alrighty. Alrighty, let's start the first one. The directions are 10 meters due north. Alrighty. I like this one. 10 meters due north. So I think 0x hat plus 10 y hat. No trig. 15 meters, 30 degrees east of north. North towards the east, 15 degrees. I'm sorry, 30 degrees. So that seems to make the most sense to me. So 15 sine 30, 15 cosine 30, both positive. So 15 sine 30 x hat plus 15 cosine 30 y hat. Writing that specifically to ensure that we lose this idea that x always goes with cosine and y always goes with sine. Choose carefully, but there's really no reason to get them all locked in like that. So 7.5 x hat plus 12.99 y hat. Next vector. 8 meters, 20 degrees west of north. Start at the north, turn towards the west, 20 degrees. My vector's 8 meters long. This is 20. So one component there, one component there, second quadrant, so my x component's negative. The y will be 8 cosine 20, 8 sine 20. So 8 sine 20. Negative 2.74 in the x hat direction plus 7.52 in the y hat direction. And finally, 12 meters, 89 degrees south of west. 12 meters, 89 degrees to the south from the west. My triangle is challenged, but I'm doing my best. It's not really looking right, but it's going to have to do, so I have some place to write. So, and it was 12 meters long. So this will be 12 cosine 89 degrees. That's in the x hat direction. And 12 sine 89 degrees. That'll be in the y hat direction. Both of these need to be made negative. So 12 times the cosine of 89 degrees is negative 0.209 x hat. 12 sine 89 degrees minus 11.998 y hat. All right, 4 vectors. I now must sum them. Oh well, I'll just put that up there at the top. Doesn't matter what order I add. Alrighty. So, add them all up. 12.99 plus 10 plus 7.52 minus 11.998. 18.512 in the y hat direction. All right, going on to the other one. 7.5 plus 0 minus 2.74 minus 0.209 gives me 4.551 in the x hat direction. That is the result of adding all those together. So now I must go. Let's go ahead and start with, I don't know. Let's go 18.512 in the y direction and 4.551 in the y direction. My result, in the x direction. That's my result. So 18.512 and 4.551. I need this angle. No better way to do that than tangent. Tangent of tangent of theta will equal opposite over adjacent. So I need the inverse tangent of 4.551 divided by 18.512. I found that theta equals 13.8 degrees. I need to figure out the length of that vector. I'm going to go with Pythagoras. So 18 squared and 4.5 squared. So 18.512 squared plus 4.551 squared to the 0.5 power gives me 19.06 meters, 13.8 degrees east of north.